Hello. In this class, we shall see how the magnetic field of the Earth can be mapped and locate the neutral points, which are the points in the region surrounding a magnet where the resultant magnetic field is zero. Some of you might have done this in your laboratory, in the school, in the laboratory, in the physics laboratory. Some of you might have done this experiment, mapping of magnetic field. So let us see what are the different possible orientations of a magnet and how the null points can be located in each and every case. So let us first consider a magnet placed on a piece of paper with the north pole of the magnet pointing towards the geographic north pole. The north pole of the magnet pointing towards the geographic north pole. You know that this is the direction of the Earth's magnetic field. Now we will draw the axial line and the equatorial line for that magnet. So this is the axial line and this is the equatorial line of that magnet. Now let us draw the magnetic lines of induction. You know that all magnetic lines of induction travel from the north pole to the south pole externally. So we will draw lines of induction which start from the north pole. It's not starting, externally they travel. I have told you that there is no starting or ending point as far as the magnetic lines of induction are concerned. So they travel from the north pole to the south pole externally, like this. They are traveling from the north pole to the south pole. So this is the direction of the magnetic field due to the magnet. Now you look at the axial line of the magnet. Along the axial line you find that both the fields are in the same direction, both the B and BH. B is the magnetic field due to the Earth and B is the magnetic field due to the magnet and BH is the magnetic field due to the Earth. Both are in the same direction. But you look at the equatorial line or the perpendicular bisector. They are acting in opposite directions. B is in this direction and BH, as always, is towards the geographic north. So this is the direction of BH and this is the direction of B along all over the equatorial line. So all over the equatorial line the two fields are opposing each other. The mere opposition of the two fields does not guarantee the formation of a neutral point where the resultant field is zero. They should be opposing each other, at the same time their magnitudes should also be equal. And when you walk along the equatorial line, near the magnet, the field due to the magnet is much stronger. And as you move away from the magnet along the equatorial line, you will find that the field due to the magnet decreases. And at a particular point, say somewhere here, the two fields become equal. Already they are opposing each other. Now we find a point, we reach a point while walking along the equatorial line where the two fields have equal magnitudes. So the resultant field there will be zero, and that is your first null point. Similarly, if you walk along the line, equatorial line towards this direction, you will come across another point, similar point, where the resultant field is zero, and that is your second null point. So you find that there are two null points on the equatorial line on either side of the magnet. One on this side of the magnet towards the right side of the magnet, and the other one towards the left side of the magnet where the two fields are equal and opposite. So if you place a magnet on a piece of paper with the north pole pointing north, there will be two null points. Both of them will be formed on the equatorial line. Okay. Now let us suspend the magnet freely by using a thread. You know that every freely suspended magnet will come to rest with the north pole, with the particular end of the magnet always pointing towards the geographic north pole, and that end we call the north pole of the magnet. So if you suspend a magnet freely, it will always come to rest along the north-south direction. So in the case of a freely suspended magnet, the null points will be again on the equatorial line, because that is very much similar to what we have seen here. But the difference is that in the case of the freely suspended magnet, you can draw infinite number of null points because there are infinite planes. By placing the magnet onto a piece of paper, you have restricted the plane to one. But if you suspend it freely, there are infinite such planes, and on each plane you can draw an equatorial line. And on each equatorial line you will have two null points. Since there are infinite planes, infinite equatorial lines, and infinite number of null points can be obtained. So remember, when you suspend a magnet freely, there will be infinite number of null points. Now let us consider the same magnet with its south pole pointing towards the geographic north pole. So the same magnet placed on a piece of paper with its south pole pointing towards the geographic north. This is the direction of the Earth's field. So as previously done, we will draw the equatorial line as well as the axial line for the magnet. Now let us draw the magnetic lines of induction. As we know, they travel from the north pole to the south pole externally. As we know, they travel from the south pole to the north pole externally. So they travel from the south pole to the north pole externally. And this time, when you look at the equatorial line, you will find that the two fields are in the same direction. This is the direction of the Earth's field, and this is the direction of the field due to the magnet. So they are aiding each other all over the equatorial line. But when you look at the axial line, you find that they are opposing each other. This is the direction of the field due to the magnet, and this is the direction of the field due to the Earth. This is our BH and this is B. Again, when we reach here, we find that this is BH and this is B. So they are opposing each other. So all over the axial line, the two fields are opposing each other, whereas all over the equatorial line, they are aiding each other. So the null points will be formed on the axial line. And how many of them will be formed? Near the south pole, somewhere here, we will get one null point, and near the north pole, somewhere here, we will get another null point. So two null points will be formed along the axial line, one near the south pole and one near the north pole. This is the situation when the magnet is placed on a piece of paper with its south pole pointing towards the geographic north. Now let us see where the null points are formed when a magnet is kept in a vertical position. Vertical position means so far we were keeping the magnet like this. Imagine that that is our north. So then, and if you assume that this is the north pole of the imaginary magnet, then north pole was initially pointing towards the north. Then it was the south pole that was pointing towards the north. Now we are going to keep the magnet in a vertical position like this. So this is what is meant by vertical position. Then the north pole is still there. Geographic north is still there. And the north pole of the magnet is now pointing upwards. So remember this very clearly. This is the position of the magnet. The north pole is pointing vertically up. The geographic north pole is still there. And we are going to find where the null points are formed. So I am keeping the magnet in a vertical position on a piece of paper. So on a piece of paper, I have kept the magnet in the vertical position with the north pole pointing vertically upward. And the geographic north is here. And the geographic south is somewhere here. So let me draw the lines of induction. So this is how the lines of induction are traveling. Again, here also they are traveling like this. So this is our diagram. So the lines of induction as usual travel from the north pole to the south pole externally. Now this is the Earth's field. Earth's field is pointing towards the north. Here also it is pointing towards the north. So this is our geographic south, this is geographic north. So the lines of induction are traveling like this. Now look at the southern side of the magnet. On the southern side of the magnet, the two fields BH and B are opposing each other. So we will have a null point here. On the northern side of the magnet, the two fields are in the same direction. Now look at the northern side of the south pole. Near the north pole, we were looking at the southern side. Now near the south pole, look at the northern side. The two fields are opposing each other, which means that you will have another null point somewhere here. So the first null point was here, and the second null point is here. So when the magnet is kept in a vertical position, you will have two null points. Two null points can be formed, but only one will be obtained on the paper. So there is a difference between the number of null points that can be formed and the number of null points that can be obtained. So here the number of null points that can be formed are two, one here and one here. Near the north pole, the null point will be on the southern side, and near the south pole, it will be on the northern side. Clear? But only one will be obtained on the piece of paper. So the number of null points formed is 2, and the number of null points obtained is only 1. Okay. Now we shall discuss 3 very important quantities called magnetic induction, whose symbol is B, magnetizing field or magnetizing field strength H, and intensity of magnetization. Intensity of magnetization symbol is capital M. If you want, you can use I also, but IV normally use the symbol IV normally used for representing electric current. That is why I have opted for capital M. So these are the 3 quantities that we are going to consider right now. We start with the intensity of magnetization. So intensity of magnetization is the magnetic moment developed per unit volume in a material. So the intensity of magnetization is given by magnetic moment developed per unit volume. What is the SI unit of intensity of magnetization? This is equal to unit of magnetic moment is ampere meter square, and that of volume is meter cube. So this is equal to ampere per meter. So the SI unit of intensity of magnetization is ampere per meter. Now let us see how these 3 are related. The resultant magnetic field present in a material when it is placed on an external magnetic field is the sum of the external magnetic field applied and the magnetic field produced inside. So B is actually, that is the resultant field produced inside the sample, inside the material. B is proportional to the sum of H and M, or we can write B equal to mu 0 into H plus M. Now M is known as intensity of magnetization. The intensity of magnetization is related to H as M proportional to H, or M equal to a constant chi into H. This constant chi is called a magnetic susceptibility. This is permeability, mu is permeability, and chi is susceptibility. So let us substitute chi H for M here. So what we get will be B equal to mu 0 into H plus chi H. So this is equal to mu 0 H into 1 plus chi. So B equal to mu 0 into H into 1 plus chi. Now when you go to vacuum, there is no intensity of magnetization. So in vacuum there is no M, which means that in vacuum B will be equal to mu 0 H. So that is the relation between all the 3 quantities: magnetic induction, magnetizing field, and intensity of magnetization. Now let us look at the classification of the magnetic materials. All magnetic materials are classified into 3 categories. Number 1 dia, number 2 para, and number 3 ferro. So these are the main classification of magnetic materials: diamagnetic substances, paramagnetic substances, and ferromagnetic substances. So we start with the dia. These are substances which experience a weak force of repulsion when placed in an external magnetic field. So remember, for a substance to show magnetic properties, the magnetism shown by matter is due to the magnetism shown by its atoms and molecules, and the magnetism of atoms is due to the orbital motion and the spin motion of the electron. So a substance can show magnetic properties in 3 different ways. They are the presence of an unpaired electron, number 2 the contribution by an orbital electron, presence of an unpaired electron, contribution by an orbital electron, and non-cancellation of the magnetic moments of the individual atoms. So these are the 3 possibilities or 3 possible ways by which a substance can become a magnet. They are, I will repeat: presence of an unpaired electron, contribution by an orbital electron, non-cancellation of the magnetic moments of the individual atoms. If any one of these 3 is present, the substance will show some kind of magnetic property. when an electron is revolving in an orbit, it will have both orbital angular momentum and magnetic dipole moment. We know that a revolving charge is equal to a charge in revolution will produce a current called equivalent current, and that equivalent current is given by a revolving charge into frequency. So when the electron is revolving in an orbit around the nucleus, it will produce a current called the equivalent current, and associated with this there will be a magnetic dipole moment, and along with that the electron, as it is in a state of revolution, will have an orbital angular momentum also, and the two are related as the magnetic dipole moment due to the orbital motion is equal to E by 2m into orbital angular momentum. So this is the relation connecting the magnetic dipole due to orbital motion and the orbital angular momentum. Similarly, the electron has spin motion also. So associated with the spin motion, it will have a magnetic dipole moment and again an angular momentum. And the two are related as magnetic dipole moment due to spin motion equal to E by m into spin angular momentum Ls. So the net magnetic moment of the electron will be m is equal to mo plus ms. And that can be written as this is equal to E by 2m into LO plus E by m into S. So upon simplification you will get E by m into or E by 2m into S, E by 2m into LO plus 2S. So this is the net magnetic moment of the electron, considering both the orbital motion and the spin motion. Now if we neglect the spin motion, then the electron will have a value or a minimum value for its orbital angular momentum. So the minimum magnetic moment possible due to the orbital motion alone, that is given by EH by 4 pi m, and this is called a Bohr magneton. So Bohr magneton is the minimum magnetic moment possible for an electron due to the orbital motion alone, and that is given by EH by 4 pi m, and this is a constant and its value is given by 9.27 into 10 raised to minus 24 ampere meter square. The value of the Bohr magneton is given by 9.27 into 10 raised to minus 24 ampere meter square. So in the case of a diamagnetic substance, there are no unpaired electrons. There is no contribution by the orbital electron, and moreover that there is cancellation of the magnetic moments of the individual atoms. All the individual atoms have magnetic moments, but unfortunately all of them get cancelled due to when you add them vectorially, you will find that the resultant magnetic moment of the sample is 0. So that is what is a diamagnetic substance. So when you place such a diamagnetic substance in an external field, a magnetism will be induced in it in the opposite direction to which the field is applied. The magnetic field developed inside the diamagnetic substance will be directed opposite to the external field applied, and therefore it will experience a weak force of repulsion in an external field. And further, when a piece of diamagnetic substance is suspended in a uniform magnetic field between the pole pieces of a magnet, it shows a tendency to move from the strong field to the weak field. When a diamagnetic substance is suspended in a non-uniform magnetic field, it shows a tendency to move from the strong field to the weak field, or it will remain with its long axis. When suspended, it will remain its long axis perpendicular to the direction of the magnetic field. Suppose we have a magnetic field directed from left to right, like this, and if this is a diamagnetic substance, and if I suspend it like this in the magnetic field, it will rotate and align itself in such a way that its long axis is perpendicular to the magnetic field. So they generally have a tendency to move from the strong field to the weak field if suspended in a non-uniform magnetic field. And suppose a diamagnetic substance is placed in an external field, then the magnetic lines of induction, they tend to move away from the magnet, or the separation between most of the magnetic lines of induction will be traveling outside through the environment and avoiding the magnetic sample. So it is like this. So they are coming like this, and when reach the air, they will have a tendency to move like this. So majority of them will travel like this. When placed in a uniform magnetic field, the tendency of the external magnetic lines of induction will be to avoid the sample as they come closer to the substance. So this is how the magnetic lines of induction travel when a piece of diamagnetic substance, this is a diamagnetic substance, is placed in an external magnetic field. So this is the direction of the external fields. So that some of them may travel within the sample also. Some of them will take a path through the sample also. But majority of them will avoid the sample while approaching it. So this is how the magnetic lines of induction travel when a piece of diamagnetic substance is placed in an external magnetic field. And more things regarding facts regarding diamagnetic substance are both M and H are oppositely directed. M and H are oppositely directed, opposite. Therefore, the relation between them, chi equal to M by H, will be slightly negative, very small and negative. Chi, magnetic susceptibility, will be negative and very small. And there is a relation between chi and mu, which is given by mu r equal to 1 plus chi. Since chi is less than 1, chi is negative and small, mu r will be less than 1. So in the case of a diamagnetic substance, chi will be magnetic susceptibility will be negative and mu r will have a value which is less than 1. Okay. Next one is the paramagnetic substance. So paramagnetic substances are those substances which when placed in an external magnetic field experience a slight force of attraction. So these are substances contrary to what the diamagnetic materials were experiencing, which was slight repulsion. The paramagnetic substances will experience a slight force of attraction. You know that in a paramagnetic, when you look inside a paramagnetic sample, you will find that a large number of individual molecular magnets are there, but all of them are randomly oriented. This is what you see when you look inside a paramagnetic material at room temperature. There are many individual molecular magnets, but all of them are randomly oriented so that the net magnetic moment is zero in the absence of an external magnetic field. But when we apply an external field, the external field will apply a torque on each of these individual molecular magnets so that all of them will align in the direction of the external field like this. So all the molecular magnets which were randomly oriented previously will now be aligned in the same direction as that of the applied field, because the applied field has generated a torque on each of these molecular magnets. So they experience a weak force of attraction when placed in an external magnetic field. Clear? So what it means is both M and H are in the same direction. M and H in the same direction. Both M and H are in the same direction. And therefore, chi will be positive, chi equal to M by H. This is positive and very small. Chi is small but positive, unlike the case of diamagnetic substance where chi was negative. Here both of them are in the same direction, then therefore chi is positive. And you know that mu r equal to 1 plus chi. So mu r will be small but it will be greater than 1. So mu r is greater than 1 but it is also very small. Now when a piece of paramagnetic material is suspended in a non-uniform magnetic field, they have a tendency to move from the weak field to the strong field. Remember, the diamagnetic substance was showing a tendency to move from the strong field to the weak field. Here it is the opposite. These paramagnetic substances show a tendency to move from the weak field to the strong field. So if suspended in a uniform magnetic field, they will align with their long axis parallel to the magnetic field. Previously, the diamagnetic substances was aligned like this, with its long axis perpendicular to the magnetic field. Imagine that the field is from left to right. But if you suspend a paramagnetic material, it will align with its long axis parallel to the external magnetic field. Now the paramagnetic properties are temperature dependent. You know that the paramagnetic susceptibility chi is proportional to 1 by T, or chi equal to C by T, where C is a constant. So this C is a constant called Feeri constant, and the paramagnetic susceptibility and temperature are related through this equation, chi is equal to C by T. Now when we change the temperature, that is either increase or the decrease of the temperature, decrease the temperature, the molecular magnets which were randomly oriented becomes more and more aligned in the direction of the external field, and when all the magnetic dipoles are aligned in the direction of the field, the saturation, we say that the saturation is achieved. So there is no more increase in the magnetic moment, and beyond that saturation, this Curie's law is not valid. So the Curie's law is valid only up to the point of saturation. Clear? Now finally we look at ferromagnetic substances, or the property called ferromagnetism. See, the ferromagnetic properties are due to spontaneously magnetized regions called domains. As we have seen in the case of the paramagnetic substance, there are large number of individual molecular magnets, but the difference in the case of ferromagnetic substance is that these individual molecular magnets are aligned along a particular direction in different regions, or there are different regions within the substance, within the ferromagnetic sample, where these molecular magnets are oriented along a particular line, particular direction like this, and these spontaneously magnetized regions will have a net magnetic moment of their own, and these are called domains. So domain structure is actually a property of ferromagnetism. No other type of magnetic material show this property. So these are the regions which we call by the name domain. So see, in each domain the molecular magnets are aligned along a particular direction. All of them are aligned along a particular direction. So the strong attractive force is experienced by the ferromagnetic substances when placed in an external magnetic field. And what are their properties? When you suspend a ferromagnetic substance in a non-uniform magnetic field, it tends to move from the weak field to the strong field. That is the same what we have seen in the case of the paramagnetic substance. Similarly, they will align with their long axis parallel to the magnetic field. And you know that both M and H are in the same direction. Chi equal to M by H, and M is much greater than H. Therefore, chi has a higher value. So it is greater than 1 and it has a higher value, and we have mu r equal to 1 plus chi, and mu r also assumes a very high value. So both chi and mu r are greater than 1, and they have comparatively higher values to paramagnetic substances. So these are the properties of ferromagnetic substances. So remember, the important point in a ferromagnetic substance is the formation of the regions called domains. Each domain is of length approximately 1 millimeter, and approximately there are 10 raised to 11 atoms in each domain. And finally, the value of mu r, the value of chi here is around 10 raised to 3. So chi has such a higher value when compared with the case of the paramagnetic substance. Both chi and mu r, both of them are very high in a ferromagnetic substance. So here I have shown how the magnetic lines of induction travel through the body of a ferromagnetic substance and a paramagnetic substance. This is a ferromagnetic substance and this is a paramagnetic substance placed in an external magnetic field. And as you see, the separation between the lines of induction decreases as they pass through the body of both the para and the ferro, indicating that the field inside is greater than the field outside. You know that paramagnetic substance, in the case of the paramagnetic substance, the field inside M is greater than H. And in the case of the ferromagnet, and these substances, paramagnetic substances experience weak force of attraction. But in the case of the ferromagnetic substance, they experience strong force of attraction in an external field. And therefore, the separation between the lines of induction is an indication of the strength of the magnetic field. So here, the separation inside is less than the separation outside. And here, the separation inside is much less than the separation outside, indicating that the field inside here is much stronger than the field outside. Here also the field inside is stronger than the field outside, but here it is very highly. The inside field is much higher than the field outside. That is why that we can observe by looking at the separation between the lines of induction as they pass through the body of the ferromagnetic substance. So both in the case of para and ferro, the lines of induction come close as they pass through the body of the material. But here they come very close, and here also they come closer, but not as much close as they were when they were passing through the body of the ferromagnetic substance. Now you know that in a ferromagnetic substance there are spontaneously magnetized regions called domains, and there are domains in which in these domains the magnetic molecular magnets are oriented. In one domain they are oriented along one particular direction, but in different domains they are oriented along different directions. Now when we apply an external magnetic field, those domains in which the molecular magnets are aligned in the direction of the external field begin to grow in size. So those domains in which the molecular magnets are aligned in the direction of the applied field begins to grow in size, and those in which they are not aligned in the direction of the applied field begins to decrease in size. So what happens is, after some time, some of the domains will have grown in their size, and some of the other remaining domains would have decreased in their size. We shall now draw a graph between the intensity of magnetization and the magnetizing fields. So let us draw a graph between the intensity of magnetization on the y-axis and the magnetizing field strength H. We know that this symbol used was M. We have been using the symbol M for intensity of magnetization, not I. So we know that M proportional to H. So naturally when H becomes 0, M should also become 0. But that is not what we observe. So this is how the graph between M and H looks like. This is the graph between M and H. From this graph you see that as H increases, M also increases, then reaches a particular value. Then thereafter, if you decrease H, M goes back along a different line. So even when H becomes 0, M has not become 0. So even in the absence of the external field, some magnetism is remaining in the sample, and this is called residual magnetism or retentivity or remanence. This is called retentivity or remanence. So that is the residual magnetism in the sample in the absence of an external magnetizing field. Now if you want to remove this residual magnetism completely, you must apply a magnetic field in the opposite direction. And from this graph, this OA is our residual magnetism, and this OB is the reverse magnetic field to be applied, so that the residual magnetism is removed completely, and that is called coercive field strength, OB. This is called coercivity or coercive field strength. So coercive field strength or coercivity, they are the reverse magnetic field to be applied so that the retentivity can be, or the residual magnetism can be removed completely. So what this graph says is this: in order to rotate the individual molecular magnets and align them in a particular direction, work is to be done by an external field, and the work done to rotate these molecular magnets will not be recovered completely when the external field is removed. And the work done per cycle, or this work done, or there is a loss of energy. When the work done is not recovered fully, what it means is that there is a loss of energy. And by calculating the area of this loop, we can find out the loss of energy per cycle when a magnetic material is subjected to a complete cycle of magnetization. So when a magnetic material is completed to a full cycle of magnetization, there will be loss of energy per cycle, and the loss of energy per cycle can be calculated by calculating the area of this loop. The phenomenon of lagging of M behind H is called magnetic hysteresis. Here I have drawn the hysteresis curves for two materials. The one that has a smaller area is for soft iron, and the one that is having a larger area is for steel. Now let us compare these two hysteresis curves. Right at the beginning itself, we can see that the area of the hysteresis loop for soft iron is less than that for steel, and the area of the hysteresis loop, as we have seen, gives you the energy loss per cycle when a magnetic material is subjected to a complete cycle of magnetization. And in the core of transformer and dynamo, in the case of the transformers and dynamos, the core will be subjected to repeated cycles of magnetization. So that is why soft iron is preferred over steel in making the core of transformer and dynamo. Now when you look at the diagram, you can see that the coercive field strength, which is this, the length of this portion on the x-axis, negative x-axis, the coercive field strength is more for steel than for soft iron. That is why steel is preferred over soft iron for making permanent magnets. So in a permanent, when you make a permanent magnet, even the absence of the external field, the magnetism should remain in the sample. So steel is preferred over soft iron for making the permanent magnets. And finally, for a given edge, if you draw a parallel line parallel to the y-axis, you will find that for a given edge, M is more for soft iron than for steel. For a given edge, this line has the same edge all over it. So for a given edge, M is more for soft iron than for steel. Yes, so M is more for soft iron than for steel, and therefore soft iron is preferred for making electromagnets. So even though steel has a higher coercivity than soft iron, the materials which are preferred for making permanent magnets are alnico, which is a combination of aluminium, nickel, cobalt and copper, alnico and alini. So these are the substances, these are the compounds which are usually used for making permanent magnets. So a permanent magnet should have a high value for retentivity, and both for retentivity and coercivity the values should be very high. That is why we prefer alnico and alini over steel to manufacture permanent magnets.